Intermodulation is the most annoying RF signal interference. Today we are explaining the mysterious root cause and how to avoid it. In this video we are explaining how intermodulation is causing interference in wireless communication, and we are showing what can be done about it. Development engineers are trying to make devices as resilient as possible, and regulatory authorities are coordinating frequency plans for minimum interference. But still, intermodulation interference between radio services is annoying us sometimes. We created an earlier video about channel interference and receiver blocking. So be sure to subscribe to the channel and watch the other video. Interference caused by intermodulation is pretty mysterious. In addition to the desired signal, there are at least two other signals involved, but it could be many more. As long as the received signals are below a certain level, we can expect reception without interference. However, as soon as this level is exceeded by one of the signals, suddenly new signals on new frequencies are appearing. In our example, unfortunately, they are superimposing the used channel. This signal doesn't actually exist in the air, it's generated in our receiver. You must not exceed the in-band signal strength of -43 dBm as a typical limitation to avoid intermodulation. So, relatively weak signals could cause that problem. Special receivers, for example for a radio telescope, are even much more sensitive. We will make a separate video about that. To illustrate this, let's use the freeze formula once again. A transmitter radiating 20 dBm, which is common for Wi-Fi devices, could generate an interfering signal of -40 dBm from 10 meters distance. With 40 dBm, which equals 10 watts of radiated power, it would be 100 meters. It's obvious that we need to be cautious whenever intermodulation products with other signals could fall into the receive band. What is the reason why a radio receiver is so sensitive to this? Let's take a closer look at the characteristic of an amplifier. In the ideal case, the output signal is equal to the gain A times the input signal. Even when the characteristic is curved towards the end, the calculation is correct as long as the input signal is small. If we are driving the amplifier to a higher level, we have to take that non-linearity into account, however. We are approximating it using a Taylor series, and in the next step we are revealing the secret of the intermodulation products. On the channel we are talking a lot about radio signals for which we need high-quality printed circuits. Check out PCBWay, the sponsor of this video. The company is covering everything you can imagine on PCBs. There are particularly interesting offers at the moment because PCBWay's 10th anniversary is coming up. Congratulations from Electronics Unmasked. Take the easy way with PCBWay. We are looking forward to continue our good cooperation. Back to intermodulation. For strong signals, we are now applying this non-linear function instead of the gain factor. You might be thinking now, oh dear, nonlinear stuff is getting complicated. But don't worry, we won't overdo it, and I will explain things in a way that is easy to understand. We need to look at the signals in the time domain, and we are choosing Euler's form to do the math. Leonhard Euler, who lived in the 18th century, derived the theorems without knowing today's intermodulation problems. You could choose the sine and cosine representation instead, but using Euler's form we are saving effort. At the receiver input, the two signal voltages are adding up. We insert the sum signal U input into our nonlinear amplification function to calculate the output signal. The first term with the factor A1 gives us the linear parts. The quadratic components are containing double frequencies and the sum. The third order components are yielding 3 times the frequencies and the differences in many combinations, which I cannot write down all here. Quadratic and cubic factors in the amplifier characteristic are actually creating new frequencies. We carried out the math up to the third order only. In practice, intermodulation products up to the fifth order are occurring actually. Next, I would like to draw your attention on another very interesting detail. Even when the factor A3 is small, the intermod product amplitudes are getting significant because these terms are increasing with the third power of the input voltage. They are increasing disproportionately compared to the wanted signal. Let's draw that characteristic into our graphic too. The third order products are only starting at a high input signal. Its characteristic is steeper, however, and theoretically it intersects the amplification characteristic. This is called the third order intercept point, which is a quality indicator for the linearity of an amplifier. The higher the intercept point, the better the amplifier. Out-of-band signals are attenuated 30 dB by the band filter, meaning the intermodulation resilience is increasing to -13 dBm. Unfortunately, this value is often reached when strong broadcast stations, radar signals or simply smartphones are near a receiver. A UHF radio transmitter at 500 MHz is radiating up to 80 kW, which is 79 dBm. Let's calculate the received power in a distance of 1 kilometer. Oops, it's 7.41 dBm. This is already well above the out-of-band limit, even when you are losing some dBs because your receiver antenna is not tuned to that frequency. So in case we are unlucky with the frequency of a second strong signal, the broadcast station could interfere on practically any frequency band on our receiver. Given the large number of radio services existing, intermodulation products are a major challenge, as hundreds could appear. The insights and measures. No doubt, increasing the distance to an interfering source is always good. Filters, frequency-selective antennas and directional antennas reducing the strength of unwanted signals have a disproportionate improvement effect due to the steep characteristic of the intermod products. If, for example, we can reduce the level of an interfering signal to a fifth, then the strength of the third order intermod products would already be reduced by a factor of 125. Mounting the transmit antennas on the same pole can be an option, because it ensures a good useful signal at the same time when a strong interfering signal occurs. In this way, we are always having a large signal to interference ratio to the intermod products. You might find a high-quality preamplifier that can handle stronger signals, resulting in higher intermod resilience. Choosing frequencies wisely so that strong transmitter intermod products cannot fall into the band of sensitive receivers is a very good idea, but there is usually not much room for maneuvering. We need to rely on the regulatory authorities that are coordinating the frequencies. I have one more tip in case you like to investigate further scenarios. In an earlier video, we presented an Excel tool to calculate potential interference. Now, stay tuned and don't forget to support the channel. See you soon in the coming episodes.